Yeah, I just alone. I think it is. Hi, everyone. I am Noman Bashir. I did my PhD at UMass, but I am currently at MIT. My role over there is Computing and Climate Impact Fellow, and that is part of a MIT Climate and Sustainability Consortium. And also, I am part of MIT CSAIL lab on computer science and artificial intelligence laboratory with the computer architecture group led by Cristina Delamitro. So today I am going to talk about sustainable computing and leveraging computing for sustainability. So first before I go into the details or the content of the lecture, I will provide a brief overview of my research work, and that will give you a context of both computing, like sustainability of computing and computing for sustainability. So if I look at the computing various life cycle phases for computing, it can be decoupled into like these kind of four things, where the first one is supply chain of data centers and servers and your phones, where basically you extract raw materials and you process them, you manufacture servers and different kind of like computing hardware, and then you transport them to the server data centers where they are deployed, or like to other distribution centers where people buy cell phones or whatnot. Then it comes to the data center edge or device phase of the life cycle. Over there, you have some software that is running, and then that software consumes some energy, and that energy consumption results in some amount of carbon emissions or overall GHG emissions, greenhouse gas emissions emitted. And once this operational phase for a device is over, it goes to end of life, where it may be recycled or discarded, or like some kind of end of life action happens to it. Now, all of this computing powers different applications in different domains of life. So here I will provide like brief overview of what kind of work I have done in all of these like different phases. So first, work in this domain for me lies in kind of, so whatever emissions or energy usage happens during the supply chain or manufacturing phase is called embodied emissions. And whatever happens in the operational phase is called operational emissions. So one of my work looks at how to basically measure or account for the embodied emissions better, and how does embodied emissions or emissions during this phase compare with operational, how to think about them, how to properly optimize them. Then within the operational phase, my work lies in kind of like four distinct areas. So first one is kind of like vision, where it's not computer vision. It basically means that how to think about sustainability of computing. What does it mean for computing to be sustainable? So some of the papers on enabling sustainable clouds, what is sustainable computing, and how does carbon efficiency differs from energy efficiency, and how does energy efficiency differs from software's algorithmic efficiency. So it's basically very high level set of papers that force you to think about sustainable computing. Then there are some work that provide insights into how to go about making computing more sustainable. So that body of work is basically limits and benefits paper is the one that looks at, okay, by doing something in the computing's this operational phase, how much carbon emissions or energy consumption of computing workloads can be reduced. So what are the limits on it? Can you completely eliminate it? If not, how much can you do by leveraging different techniques? Then similarly, there are other papers that look at, okay, what if you use this signal for carbon intensity versus that signal, and so on. Then there is work on developing carbon-aware optimization algorithms, which is a couple of papers at Sigmatrix, which basically look at how to run machine learning workloads in a carbon-aware manner. So if you have a ML training workload, you want to ideally run in when the carbon intensity is low and pause them when it is high. So, but how do you know that this is low enough, or there is a cost to switching? How do you balance the cost of like checkpointing and restoring and wasting energy there versus the carbon savings that you get by doing that? So it looks at, and these couple of papers basically look at these algorithmic aspect of carbon aware optimizations. So now let's say you have these carbon aware algorithm that allows you to run your training workloads in a carbon aware manner, but you need actual systems where you can deploy those. So in currently basically out of the box cloud operators do not provide you this functionality to be carbon aware. At best, they just like give you visibility into the carbon footprint, and that is even like they would tell you, for example, GCP and AWS would tell you how much carbon your workload consume at the end of your billing period or something. It is not live. So now you need systems where you could actually do these kind of optimizations. And over there, we developed a couple of papers where we developed a Slurm-like scheduler. You may have heard of it, which just schedules batch jobs. So we developed a green version of it. Then there was this ecovisor akin to a hypervisor, which tries to incorporate energy and carbon efficiency constraints. And then there is carbon containers work, carbon scaler, which works with scalable workloads. So basically, this bunch of work is about enabling applications to be carbon efficient. Then I have a couple of other work that purely focus on software or energy efficiency. So one of my salient works was overcommitment in data centers. So this was the work that I did as an intern at Google, where we looked at to increase the utilization of servers. You basically schedule more jobs than the server's capacity, which is called overcommitment. But you want to make sure that even when all the jobs run at their max capacity, they don't violate the physical machine's constraints, because otherwise you will have to evict them. And now this work is the default overcommitment strategy inside all of the Google data centers. And then there is some work on managing electrical and thermal energy in energy systems, power monitoring, and in cloud you have these different kind of basically you have different contracts like on demand, spot versus reserved, which gives you different guarantees and also like different price models. So when you have a certain type of workload, you want to balance basically the cost versus wait time, how long you have to wait to get the lowest cost, and so on. So basically this body of my work lies in that. Okay, then some of my earlier work during my PhD, and mainly most of my PhD, like this is the work that I did in the last 2 years or so. That work is what I did during my PhD, which was how to use computational methods to decarbonize different societal sectors, be it building, transportation, or integrating more renewable energy into the grid, and so on. So yeah, that work I will maybe go into some of the details. And my recent work at MIT has looked at the generative AI sustainability and climate and sustainability implications of generative AI. I will touch that towards the end a little bit to talk about it more. So with my research overview, so I will go through the different slides which talk a little bit about not my work, but in general, how to think about these topics. But if you have any particular questions or you are interested in any of these works, you can ask questions during the lecture, at the end, or send me an email later on. So first thing is that computing's demand has been growing exponentially. So in this graph, I have transistors per capita as a proxy for computing demand and time on x-axis. That is on y-axis, this is on x-axis. And here I have labeled, like, so as you see that transistor per capita, like, demand has been increasing, and I have labeled kind of the major innovations over this time period. So there were, like, first major innovations were far and few in between. It took a lot of time, but after this time period, major things started happening, like, relatively frequently. And I think two of the things have contributed to the increase in computing demand. One has been this, like, smartphones, where now people have a device which needed applications, and that resulted in a lot of applications being developed, and they need to run on cloud or, like, some servers, so that, like, computing demand increased because of that. And then even that could probably not have increased it as much as I think cloud computing did, because with cloud, everyone could just rent out the servers and run their applications, and they did not need their own data center. So I think these things, along with this recent kind of introduction of chat GPT-like tools, have really increased the computing demand, and it is increasing exponentially now. And in future, there is no sign of it slowing down, because society will keep finding applications of computing in all the different domains of life, such as transportation, cities, and agriculture, and all other imaginable things. So this is kind of the state we are in right now. So what are its implications on society? So let's say you have computing, which enables societal applications, just like every domain that we discussed. So computing's energy demand goes up, and the hope is that if that computing is applied in a responsible manner, or to make other sectors more sustainable, infrastructure's energy demand would go down. So let's say you deploy a sensor here which turns off the lights when everyone leaves. So even though that sensor is consuming energy and computation that runs behind it, the idea is that the building's energy will go down. That does not happen always, but that is basically the idea behind applying computing to different things. Or you could be applying computing to increase productivity, increase leisure, and whatnot. But here we are talking about the sustainability implications. So what happens then? Once you make something efficient, it doesn't mean people start using it less. It leads to increased use of applications, and more applications are developed. Computing is applied to even more fields. And that is kind of summarized by a concept or law, which is called Givon's paradox. You can read about it more, which basically says that if you make something efficient, it does not reduce the net energy consumption. Instead, the increased demand for that mostly basically it offsets any gains that you get from energy efficiency, and the net energy consumption increases. So what ends up happening is that society's energy demand also increases, and that is what has been happening throughout human history. So basically, computing's energy demand does not lead to basically societies consuming less and less or emitting less carbon. So this is how my interpretation of the things is how they work. Okay, then the question is, now we have this exponentially increasing computing demand, how it is being served. So we have multiple ways of serving this computational demand. One of the biggest ways is data centers, which are these large buildings which house thousands of servers and data storage for example, Google has a data center which houses more than 100,000 servers and consumes 100 megawatt of power, which can power a small city, just to like give you an idea of just the sheer scale of these things. And then you have edge data centers or edge sites. Like basically edge data centers could be small edge physical data centers, or edge sites could be where a bunch of machines are placed by a roadside or something like that, which have tens of hundreds of servers and data storage, much smaller than that, much low power density, computation is low as well. Then you at the other end of the spectrum, you have mobile devices which are handheld, and ease of access, latency, and all of those things are small, but power is not being that large. Okay, so we have this computing demand, which is being served by this data centers or some form of computing. How does that result in basically cost, energy, and carbon? The first thing is basically cost is servers, buildings, and energy consumption. They all cost a lot. So you need to buy servers, you need to build infrastructure, and the operation of data centers, if it is consuming 100 megawatt of power, the bill is in billions of dollars. And then so these things go on the cost element. Then on the energy side, there are two things that go on the energy consumption. So first one is basically the compute, which needs power. Like you need certain amount of power to run your servers. That is the computational power. And then because servers are very dense and like high power consuming devices, and as you know that if some energy is being consumed and it is not resulting in a mechanical kind of process, all of that is converted to heat. So even your lights, anything, wherever you consume energy and there is no mechanical kind of motion, every single unit of that energy is converted to heat. So now you have 100 megawatt of power that is being converted to heat in a data center. You need to cool it down, and that requires energy. So in state-of-the-art data centers, there is a metric, like in general, there is a metric called power usage effectiveness, which tells basically how much extra energy you spend on cooling on top of like whatever you spend on compute. So in normal data centers, the value is around 2, which means you spend almost 50% on cooling, 50% on compute. But state-of-the-art Google or Meta and all of these data centers have a value around 1.09 or something, which means that you spend 9% extra roughly on cooling. So they are really efficient. Then in terms of carbon, so carbon emissions from this computing demand are coming from the manufacturing process, where you extracted materials. As a part of that process, some emissions were happened. Then you use electricity consumption while extracting and processing and building data servers. So there was emissions over there as well. And so that is kind of the embodied part of things. Then operational part is where you are actually using energy to run servers and like cool the facility down. So that is where the two carbon components reside. So what does it mean to be sustainable? Sustainability can take a lot of different definitions. In this case, and it like sustainability could be economic sustainability as well, that business remains viable. It could be social sustainability, that it does not lead to society being extinct or civilization being extinct. Here we are talking about environmental sustainability. What we mean by that is we impact the environment in the least amount. And even though there are different things about computing that impact environment, it is the water consumption of computing that is getting more recent attention. It is also the resource used. So let's say if silicon is being produced, it can power like small electronics that increase the basically ease in life of a person in, let's say, developing part of the world, you can use that finite amount of silicon to either do that in some cases or build GPUs. So in those cases, you are still impacting either you are accelerating the process of that extraction and impacting environment in a bad way, or you may be taking like resources from another kind of better use just because like of the economics of computing and all. I won't go into the detail, but the idea is that in this work, we just focus on the carbon or GHG emissions. And sustainability is not just that, it is much broader term, but here we just focus on the carbon aspects. So as I said in the last slide, carbon emissions happens during two phases: embodied emissions, operational emissions. We want to reduce both. And again, because the scope is high, I would just focus mainly on the operational emission side of things that basically you can control. And this is relevant because as a computer scientist, you will run workloads, you will schedule them, you will work on some aspects of it. You will not have a direct control over the supply chain and how things are manufactured. So most of this class focuses on the operational carbon aspect. So how is carbon footprint of computing could be, or the operational one, measured? So there are four elements. So one is total units of work. Let's look at from that side. So it could be that you have, let's say, 100 inference requests, and the task is face detection. So you send 100 images, and you want them to be processed and tell if you recognize that person or not. That is the workload. Then cycles per unit of work tells you to process one image, how much computing cycles you need to do. Let's take a GPU, and you can kind of like compute to process one image. You need certain number of matrix multiplications or flops or ops or whatever you can kind of like metric that you want to use. So this will give you the total number of the multiple of two things will give you the total number of cycles, computing cycles that you need to perform to satisfy this workload. Now, computing's energy efficiency, which is basically hardware's energy efficiency, it basically tells you to do one cycle of computing, how much energy you need to consume. So let's say my phone or let's say Jetson Nano or some device like that, when it runs at full capacity, it consumes 10 watt. So if it runs for an hour, it will consume 10 watt hour. So that is the energy, and whatever the workload it will do is the total number of cycles. You can divide them to get this value. So this basically tells you how much energy efficient your hardware is. And then final thing is energy is carbon efficiency. So now you found out by just these three terms that to process 100 inference requests, 100 into 10,000 by 5, 200. So basically you need 200 kilowatt hour of energy. Now the next question is, for each unit of energy used, how much carbon is produced? If it is solar, it will be almost zero because solar does not consume any fuel. If it is coal, it will be very, very high. So let's assume that it is 1 kilowatt hour per. So it is the reverse of that. So once you emit 1 gram of carbon, you produce 1 kilowatt hour. It's a hypothetical source. And this is how you can compute. The idea of telling you all of this was to give you an idea of what are the aspects about computing that you can control to basically modify the carbon footprint. I will go to a later slide first to give you an idea, and then I will come back. So here, if I look at all of those components, so first one was the total demand or total units of work. No one has incentive to reduce that demand because more demand means more money for the companies and industries and more jobs and more applications and whatnot. So that part is not going down. It is unbounded. It does not have any fundamental upper limit. Then if you look at the cycle per unit of work, which is basically algorithmic efficiency, how efficient your software is. And everyone has an incentive to improve that, because this means that you will consume less number of cycles, and less number of cycles would mean less energy, and that would mean less bills for your data center. So, but it is still bounded, because you will need some amount of cycles to process an image. It will never be zero. Then computing's energy efficiency, again, hardware's energy efficiency. You want to make it as efficient as possible because it reduces your cost. And then finally, energy's carbon efficiency. Theoretically, you can make it infinite, because if you have solar, and if you ignore whatever happened in the manufacturing, you have a zero emissions fuel, source. Then it means basically you are not emitting any carbon for whatever amount of energy you produce. So in energy's carbon efficiency becomes infinite. So you can improve that. So basically, out of these things, what you can work on or what you cannot work on, just to give you an idea. So now the next thing was, okay, what has been happening in terms of sustainability in the computing space? So we looked at these like 4 factors. Most of the work has been either on improving algorithmic efficiency or hardware efficiency. So over time, people started packing more and more transistors and started making hardware more and more efficient. So that, and also there was an effort to building large scale systems. And with large scale systems, there was an economy of scale benefits, which says that if you manufacture things in a large scale, the cost goes down, and so on. So because of that, there was a shift from these traditional small data centers that companies used to own and had a very bad kind of PUE value, to hyperscaler and cloud-based data centers, which have almost 1.1 PUE value, as I mentioned earlier. So people, even though computing demand over this period from 2015 to 2021 significantly increased, but because people were, like, the computing workload were running on a much improved or energy efficient hardware, the energy consumption did not go as high. And these are some of the trends according to like different studies. So basically, according to one study which said that from 2005 to 2018, the energy consumption only increased by 6%, while computing demand went up by 6x, which is not shown here. But there are also other studies that say this is wrong. It was much higher, and then there is a highly pessimistic version which says it was almost 5 times this value. So what does this say? It's not to say, like, it's not my job to say that which study is better. But the idea here is to convey that there are these different estimates, and companies or whoever, like a person who is trying to make a case for climate friendly policies, they will pick the worst case thing and make a point according to that. A company who wants to keep the operation going on as usual, they would pick the least value. But the idea here is that different studies estimate different things, and we could be anywhere in this range. And this is concerning, that despite massive improvements in energy efficiency, energy consumption still increased. And in future, as demand accelerates further and energy efficiency gains or opportunities lessen, this energy, an increase in computing demand will directly result in increase in energy consumption. So this is just to drive home a point that even though in the past we have able to curb the energy demand, in future that may not be the case. So this I have already gone through. So that was the energy consumption part. There was another part about making energy's carbon efficiency infinite, which basically kind of said that move to solar or some kind of renewable energy. So let's look at what has been going on in that domain. So over like 18 years from 2001 to 2017, if you look, overall energy intensity, which is how much carbon you emit per unit of energy produced, has been going down. So Europe went down, North America went down. There was a period where in the middle, like Asia has kind of the highest, but overall the world average is that. And yeah, world is like that red line in that one. So, and this straight line is 0. Basically, Asia and overall world has much higher carbon intensity, even though it is slightly decreasing, but it is higher. So what does that mean? Because there is, again, another kind of argument that because nations in the global south are behind on the development curve, they are now deploying like coal power plants and things like that to provide basic necessities of life to their people. So they get to use that versus these like countries like USA and Europe have benefited from all of the gains from coal and everything, and you cannot stop them. So that is a whole other argument, like high level. But the idea is that even if US and Europe's energy carbon intensity goes down because of more renewable integration, that may not be possible worldwide because the grids in other parts of the world are not as sustainable or reliable. And also, they have bigger things to worry about, just as providing electricity access to people. So, yeah, that is just one way of thinking it. Other people can have different view. But the point is that carbon intensity of the grid is decreasing, but it is still not decreasing and going down to 0. So before, let's say, in a future, we shift completely to a scenario where all of our energy is coming from 0 carbon resources. It could be nuclear, it could be hydro, solar, wind, or biomass, thermal, geothermal, whatever. But in the middle space, where what is happening is that we have some gas generators, some coal generators, some solar power, and some biomass, some hydro, and whatnot. And this is the result of that hybrid mix of energy resources. So the current carbon intensity of electricity varies widely over regions, across regions, and over time. So just in this graph, we see like 6x temporal variations between within a region, and 30x spatial variations between like these 2 points across regions. So what does this mean? You can, to reduce carbon footprint of energy, you would want to run, rather than here, you would want to run in this region, which is Ontario, Canada. And if you are restricted to within a given region, you would want to run your computing workloads at this point rather than at this point. And same for here, rather than at this point, you would want to run it here. So basically, you should try to run your computing workload when and wherever low carbon energy is available. Now the question is, can we do that for computing workloads? And yeah, this is just another illustration of how the world looks like in terms of the variations that we saw and the carbon intensity values. So you see, the idea behind this graph is just the key takeaway is that carbon intensity is variable across a lot of regions, and there are significant variations in the average intensity across regions. So there are plenty of options for reducing carbon footprint by running when and where low carbon energy is available. So can we do that for computing workloads? So good news is that computing's workload are uniquely flexible, and they have unique advantages. If you have a job and it arrives to a server or a scheduler, you can run it immediately. You can send it to another data center to run. You can run it a little bit later or slower. You can assign it less number of physical resources. You can assign it more resources. And you can also run it intermittently, like you can checkpoint and resume. And so basically, this is to just show that computing workloads are uniquely flexible. It doesn't mean that all computing workloads are flexible. For example, if you have a web request, that is kind of an interactive thing. You need to serve it immediately. You cannot say that I will run it after 12 hours. But on the other hand, let's say similarly, if you have a ML training, which is running on 2 TB data set or like even larger, you have to kind of run it on a given place, because sending it to another place would take a lot of time and energy in terms of network power consumption and so on. So basically, but the point is, you should identify the kind of flexibility your computing workload, a given computing workload provides, and then look at how to exploit that. Okay, so the question is, we now have two really good pieces. First one is energy carbon intensity varies, and computing is highly flexible. How do we match these two things with each other? And this is what we did as part of like this last year couple of papers, which was enabling sustainable cloud case for virtualizing energy systems. So I will just go into the detail. So if you look at how do we, like what is our relationship to the energy today, it is very, very simple. You have a plug, you plug some appliance into it, you expect power to be available unless you are from Pakistan, India, or Bangladesh. Like over there are a lot of time grid may not be available and so on. But generally, if you plug something in, you get power out. And there is an abstraction of unlimited power availability that you have never need to consider that if I plug another laptop, where would that energy come from? You just plug, it runs. So that is how most of the applications in computing or systems have been designed. So you have a data center, it connects to the grid. Software developer does not worry about the energy consumption of its software. Whenever you are writing some code, you don't think about where the energy is going to come from, where Colab is getting its energy from, or where the Unity like basically cluster is powering itself from. So you never have to worry about it. This is how the current kind of computing system has been designed, and that is just energy flows one way and applications never care about what else is there. But the reality, as we saw, is much more complex. We have in the background, the grid is producing energy from solar panels, some part, and that can have massive amount of variability, as shown by like this upper graph, where I think I have 16 different locations that correspond to 16 AWS regions. And you see like the power is highly variable over there. Then we saw this graph about grid's carbon intensity, which is saying that grid's energy mix changes over time. Then finally, in some cases, you may have battery available, which may have low or high charge available at the time. But applications never care about it. So the first rule of like people like to say that you need to know about the problem before you can do anything. So first thing is exposing visibility to applications. Applications should be able to tell, okay, how much carbon we are consuming, how much energy we are consuming. And that is kind of what these cloud providers are trying to do by telling you at the end of the month that your total carbon was this, your data flow job or BigQuery job or like EC2 instance or whatever, they consume this much power and whatnot, so that you can optimize it. So basically exposing that kind of visibility into energy system, or at least the carbon consumption, is kind of the first step. But just the information is not useful. You need to have some kind of control or some ability to change how you operate or how you use energy. Without that, you won't be able to reduce it. You would just know that how bad I am. What can I do about it? I don't know. So you need to provide some kind of control. And to give an example of this, we built a system which was called EcoVisor, and this is what its interface looks like. This looks crazy, but it's actually very simple. If you know like any kind of container management system, be it LXD, which runs Linux containers, or a Kubernetes. So this is that. It is running on a server cluster. What we are doing is we are saying to you that rather than directly submitting this job to this Kubernetes cluster, submit them to our interface, which is a wrapper around Kubernetes or LXD. What it does is that it uses all of its functionalities in terms of CPU management, GPU management, and whatnot, but it also gets information about the energy system that is powering the servers. Like it could be by interfacing with the grid or controlling charging battery and whatnot. And, and it provides additional function on top of the standard Kubernetes or LXD thing. So these are how the initial additional functions could look like. For example, it could have a set container power cap. So you could set in the past set container RAM limit, or memory limit, or CPU limit, or how long it can run, or things like that. But you can now set container power cap. You can set how much discharge you want from your battery to come from, or how much charging you need to to go towards the battery. So these may seem like a list of arbitrary functions that we have implemented, but they were after a careful design, and we found this set of functions to implement any kind of carbon aware policies for a wide range of applications. You could implement those with just this set of functions. Some of them are get, which gives you information, and some of them are set, which expose control to you over this system. And then we had two prototypes where we kind of demonstrated the fidelity of our approach. One was like this small prototype that we built where we had Raspberry Pis things, Rock 64 servers with power monitoring. And then we had we used a DC power supply with an inverter as a emulator for the grid. We had battery, and then this was a 16,000 solar array simulator, which basically replaced the traces of a solar panel. So this is kind of a mini data center that was powered by solar panel, had battery, and also had some control over the grid. And when we ran a bunch of different applications, for example, ML training or scientific application workloads, and web servers, Spark data processing pipelines, and again, stragglers in scientific computing workloads and whatnot. And we implemented this on a bigger data center as well, but we could not have like solar panels connected to it, so we emulated in that case. Here I am going to just show you the capabilities of this system in using just one of the applications that we had. So here, let's look at this. Here we have different policies or different methods on x-axis. Here carbon emissions are on y-axis, and runtime of a job is on another y-axis. So let's take a look at just this column. Carbon agnostic means that you don't care about carbon and you just run your job. When you do that, you complete kind of immediately whatever number of hours it takes, like it may be like 1 hour, let's say, and you emit a lot of carbon. And depending on when you run, that carbon can vary, because we know that carbon intensity varies. So this is just the error bar for that. Then this is a system policy, which is nothing else. It defines a threshold for carbon. If your carbon is below that threshold, it stops. If it is above that threshold, it runs. So what happens is that it only runs during low carbon periods, and as a result, its carbon intensity goes down. On the other hand, because now it is pausing during the high carbon period, its job completion time or the run time increases. So this is kind of the policy that it can implement. But there are further optimizations available. As I mentioned, that computing workload could be scalable. They could be run at a faster or slower rate. What about this idea that when the carbon intensity goes low, rather than running at 1x, we give more resources, run at 5x, 6x, whatever x. And when carbon is high, we stop. So doing that would allow us to make up for the time that we lose by suspending. So we did that. We tried different scales, 2x, 3x. We see that we are able to basically reduce the time from a pure like 1x policy to 2x and 3x. But because scaling of computing workloads is energy inefficient, when you scale to more servers, you are losing a lot of energy in communication between those servers. So because of that inefficiency, your carbon starts going up. Every additional server does not give you the same amount of normalized computing power as the previous one. And that again depends on the application, how much you get. So basically this shows that there is a optimal scale where you reduce job completion time at some cost of carbon increase, but it is still less than this. And then for a blast, which is I forgot what like the acronym for that, but basically this is a scientific computing workload, and here we see that the optimal scale is 3x. So the first idea of this evaluation was to show that you can implement carbon aware policies using our interface first. Second one was that you cannot treat all the applications the same way. They will have their own characteristics which would determine how should they be operated. And that is why we decided to expose the control to the application. But there was a fair criticism for our paper, which was that developers don't want to handle all of this complexity. They want things to remain like simple. So why don't we leave it to the system to do that task for you, the carbon reduction, and developers don't have to worry about it, which is true. As you see from this graph, you can do that, right? You can do that, but it is about kind of a suboptimal solution. System can reduce carbon for you, but it won't be able to do it to the extent that is possible because system doesn't know everything about the application, especially in the cloud settings. But if application manage, there is increased complexity, but you get more benefit. So it's kind of a trade-off. This is also a philosophy between exokernel approach and what? Sorry.
I have a question.
Yeah.
Here, the assumption seems to be like the total compute capacity in the system is unlimited. Like when you increase, here you scale one particular application. If the system is heavily loaded, of course, that would be other applications both dependent. I wonder what the overall like runtime and carbon emission would change from a global.
Yeah, sure. So there are two aspects of your question. So first here, in this, we focused on a single application and demonstrated the benefits for it. There are versions of our work that target a cluster or a bunch of job or a given workload. And then it tries to determine basically how to do carbon aware optimizations for a bunch of jobs. But obviously, you don't have infinite capacity. If during low carbon period, everyone wants to go up, you will hit a limit. Then there are two questions. First, you will have to navigate, like you will have to be fair somehow. If all of the applications or workload belong to a person, you need to find out a way which applications to run when to still optimize the overall carbon footprint. If they belong to different customers, then you have to navigate basically the issues around fairness. But why is this still possible? If your data center was saturated, that it had 100% utilization, then you cannot do anything, right? Like you are just running your workload. But our cloud data centers are not 100% utilized. currently the utilization level of Google data centers is on average around 40%. So that means there is significant headroom where you could go up and down to manage, basically to gain carbon benefits. But it is true that with some limit on the carbon capacity that you have and multiple people trying to access that capacity, there will be basically issues, and there will be further limitations on carbon emissions that you can achieve. And in some of our work, we try to kind of look at that aspect of the problem. How do things change? How much headroom impacts the carbon savings and whatnot? But generally, if you think from a cloud so also one other thing that I want to share. In writing papers or in doing any kind of research, it's very important to think, what perspective are you taking? People often kind of conflate the two things. In a cloud setting, there is a cloud operator's perspective. Cloud operator's perspective is different from a user's perspective. To me, as a user, cloud has infinite capacity. So if I am just trying to optimize my workload, I can assume that, and I can try to do that. Each job can be treated independently. Now, I understand that if I want, in peak hours, I request a lot of GPUs, cloud may deny that. And in our research, we kind of look at those denial rates and all of those things as well. But from a cloud user perspective, at least today, when not everyone is trying to be carbon aware, you are fine to go with then kind of assumption of infinite scale. But from a cloud operator's perspective, the question would become this thing, that now you have a bunch of people who all want more GPUs during noon when solar is high. Now, currently, they don't incorporate the time into their pricing model. It's very simple, like it's fixed price per unit time, but they may embed that into it. So then there will be a cost versus carbon trade-off when you are optimizing. So it's, I mean, there are multiple variants of the problem that will tackle this thing. Okay, so with computing now sustainable, we will move towards sustainability of basically leveraging computing for sustainability. So, and I will give you some example. So here I have a bunch of examples where computing can be used as a tool. So for example, for buildings and transportation system, buildings are a distributed system. You can think of them like that. You can sense and monitor energy, temperature, occupancy at different places. You can analyze the data, and then you can control lights, HVAC, those to reduce energy usage. And even in terms of distributed system, there is one other thing that is happening, and it impacts the operation of not only computing, but also the building operations and whatnot. So previously, think of this. You had cars and you had buildings. How you operate your cars was decoupled from your building use, because you just go to a gas station, you get fuel. It does not have anything to do with electricity. Now with EVs being in the picture and increasingly being more and more integrated, you will have cars when all of the office workers arrive in a building, your demand for that building or the grid around that will go up, because everyone will put their EVs into charging. When they go back at night, they will have an additional demand which was not there. So now, because of this increased electrification, we are creating more couplings between different societal sectors, such as buildings and transportation. And this is where like distributed system analysis and optimization approaches could be helpful. Again, transportation is an distributed system. I won't go into the examples, but agriculture example, I can provide a little bit more kind of example. So let's say you have, so there is a precision agriculture term, which basically tries to monitor crops at a very, very fine granular level. like they would try to monitor the temperature of the field at 1 foot granularity or 1 acre or something, like something very high resolution rather than just having like Amherst wide temperature. They would try to take pictures of the leaves and things like that. They may have a drone that goes around the field and takes pictures to identify pests and diseases and whatnot. They may have there are tractors that go through the things, the field, and then they try to spray things. So basically now you have a bunch of kind of devices that are roaming around your field, and they need to coordinate with each other. And that is where, again, your agriculture, which has been traditionally the least kind of tech heavy sector, is now being even more being techified. And then in the building monitoring, I just gave examples that you can have monitoring and then do some basically analysis on that. You can analyze that data, and you can develop modeling, analytics, and prediction pipelines. So for example, I think I gave this example at the start. You basically you can monitor the energy consumption, identify basically the times when a person was home or away, and then you can try to optimize your HVAC schedules based on that, and then the light based like control that I just said, that when everyone leaves it turns it off and things like that. Then the next thing that computing can help to advance the sustainability of other sectors is in electric grid, because renewable energy is highly variable and it depends on weather conditions. So you need more sophisticated kind of prediction approaches to predict renewable energy, so that you can, or the grid operators can plan for it when the renewable energy goes down. Because, okay, let's take a step back. Why do we need to care about this variability? Because in electric grid, for it to be viable, you need to match your generation with your demand instantaneously at every second. So if your demand is not changing and suddenly you were relying on a renewable power plant, but its power drops significantly, you need to make up for that using some other thing. And previously, these drops were not as significant. Like in the worst case, some generator will go down. But if you have a coal power plant operating, it will keep operating at the same power level. So now this is a new kind of complexity introduced into the system, where within milliseconds, your power can go up and down. You need some other generator to make up for that. Those generators don't have that much faster response time. And even if they have, there is a lag of communication signal and control signal and whatnot. So some of these things, computing methods and AI methods could help. Here we are again, this is just an example of how machine learning plus data-driven methods can be used for better forecasting. Finally, EV charging case, I think also I gave a brief example, but let's say I told you about like when people come and they charge. But let's say there are two other things that you can consider. If they are at home, you need your EV charged by, let's say, 6 a.m. when you leave for work, or 7 a.m. and you plug it in at 8 p.m. Now you have roughly 4 and 6, like 10, 11 hours to charge the battery. You can either charge your EV immediately at a full rate, or you can basically wait for the least carbon intensive slot at night and charge that. So here again, computational methods can be used to decide that. And then if you have a fleet of EVs from workers who just came to UMass, and you want to prioritize each one based on when they leave, it is similar to computing job scheduling with different deadlines and different kind of like resource requirements. So you can use computational methods to do this like scheduling. So finally, as I said, I will talk about the work that I am recently doing at MIT. And one of those like threads is looking at the climate and sustainability implications of generative AI. So this paper is supposed to come out in a week or so, and it was done with like a lot of people across different departments at MIT. So yeah, this is like, and I will talk about more. So what we are saying over there is that generative AI is growing in a kind of is experiencing an unfettered growth. What it means is that its growth is unchecked and it is increasing very rapidly. So what is the reason behind that? And this is just an example of the growth that ChatGPT reached 1 million users in 5 days, and only 15% of those users, like overall ChatGPT users, are from US, which means that it is 85% are coming from different parts of the world, and it will keep increasing. Not like if not for ChatGPT, but broader like Gen AI kind of tools, the applications and demand would keep increasing. And this is like interest graph in generative AI from Google Trends. But why is that the case? Why are we seeing this like in like trend increasing trend? So one reason is the perceived benefits. Everyone believes that generative AI will transform every single domain of our life and it will make it better. It can be applied to anything that you can imagine, and that is the sense that people have. This is the perceived benefit. We don't know if it will actually do that or not. These are not the realized benefits. These are the perceived benefits. So that hype is basically driving investors and everyone's interest, and more people are trying to kind of build these next generation models and things like that. So that is one of the factors. Second factor is this consolidation of AI capabilities. Like previously, how science progressed was there will be a person in a lab working on something. They will have limited amount of resources, and whatever they do will the progress they will make in their lifetime would be limited. Now, the good thing about consolidation of these tech power is that now, because they have infinite amount of resources and very smart personnel working for them, what ends up happening is that they have collective knowledge and they can acquire small players like Google acquire like DeepMind, Microsoft is working with like OpenAI and so on. So there is this high concentration of tech and talent, power and tech resources and all of that, and that basically creates a environment of innovation, rapid innovation, which is a good thing, but like which is a good thing from the advancement of generative AI perspective. But if you look at from sustainability perspective, that may be a different story. So this is one of the driving factors. Third one is lack of regulatory oversight. Currently, there is no comprehensive law anywhere around the world. Like there was a recent law passed by Massachusetts senator. Also, there was a recent European act. They try to govern different aspects of AI, but there is no comprehensive kind of rule or regulation that tries to do that, be it environmental impacts, ethics, or any kind of like regulation. So that also, like having no regulation means that you can pretty much do everything. And finally, efficiency improvements. So as I think I made a point that energy efficiency of computing has been increasing. How does that impact generative AI? Because the energy efficiency has improved and you can connect like these thousands of GPUs together, that allows you to train generative AI models much faster than what you would have been able to do had it costed maybe million GPUs and they could not be connected together. It would take forever to train those models. And because these like efficiency improvements in hardware, be it in terms of scalability, ease of access, energy efficiency, the price of electricity and whatnot, because that has gone down, it has become easier to train larger models. Okay, then what do we do about it? So what our work proposes is this thing, that there is a concept of life cycle analysis in basically different fields. It also applies to like computers and whatnot, which basically says that you account for the costs that are incurred over the life cycle of a product and compare it with its benefits. And if that is kind of a favorable kind of comparison, you do that. So in this work, what we say is that we should develop an evaluative framework about generative AI. What we should do is that before we apply it to any kind of application, we should try to quantify its cost and see how do the realized benefits, what is the tangible benefit that it provides. And for that, we need to do a bunch of things. We need to restrict our analysis. You cannot do an analysis for, is generative AI helpful for all applications around all cycles or all domains of life? No, that is an intractable problem to solve. But what you could do is that, which I will give an example on the next page, that maybe you could quantify for search, is Gen AI better or not? Then baselines and scenarios. You need to compare it with some state of the art. Let's say Google search is the state of the art in terms of search, and you compare it with ChatGPT search. And then similarly, you need some metrics and data and whatnot. So with that, let's go to the example, which is still not complete. But here, this paper was more of a vision paper where we proposed this idea. Now we are working on doing this actual analysis. So let's say how to do it for, just to demonstrate how would this analysis be conducted for this use case. So here, think of a user. A user has access to two tools. One is the standard search engine, Google-based. The other one is basically ChatGPT-based search. Now the question is, you have a well-defined search task, which I don't know as of yet, but it could be that find the date of birth of a person, let's say, or some random thing. That is a well-defined task that we need to accomplish. The first thing would be, okay, how many Google searches or how much time it takes for a person to find that information. That is your baseline. Then you do the same thing with generative AI and see, does that lead to the reduce? Because this is what they say in favor of ChatGPT, that because it is more comprehensive, you need to do less number of searches and so on. So you do that. You may need less number of queries. You may get it in a faster kind of like time period. So like these are the two kind of cases. Then this is a task, and now you need to quantify benefits as well as costs. So let's talk about the benefits. Benefits could be in terms of number of queries that are performed less. And because Google, let's say ChatGPT query costs 9 times or 6 to 10 times energy consumption than a standard Google search. So even if you kind of reduce that by 83%, you will have the same, let's say you do 10 queries versus 4 queries, still ChatGPT is consuming more energy. So you have to look at the energy and carbon cost of both searches. And then you also look at the benefits, which may be like the amount of time you spend. So that could be the benefit metric. Then on the cost side, you need to kind of do that holistically. So there are two types of mainly costs. One are computing related impacts, which basically include the raw material, energy, water, waste production, and GHG and gas emissions. And they happen during the whole life cycle phase of a search engine. So you will have a supply chain, servers are manufactured and whatnot. Then for Gen AI models, there was this data and R&D that may be true for search engine as well. But then you have Gen AI training, inference. So all of there are costs incurred in all of those domains. There are other potential impacts, socioeconomic impacts worldwide of computing and a user using that. So for example, if a user is using it in a job, they may be like there may be less number of jobs available for other users, or if AI chatbots overtake call center jobs, then there are socioeconomic impacts on that way. So you need to quantify whatever you can. Maybe you don't quantify these costs at present, but other costs you can fairly easily quantify. And basically, the idea is to then be able to say something about, okay, this app, you may not be able to say absolutely that this application in itself is bad, because if it reduces time even by 1%, you cannot say that if that 1% was worth it or not. But you may be able to compare different things. So you may be able to say that ChatGPT 3.5 reduces your search time by 40%, but increases carbon by 200%. ChatGPT 4 reduces time by 35%, but increases time by 400x, which means that the trade-off is not quite feasible for the 4 version. So you could be able to make some kind of assessment of different applications and try to direct your limited Gen AI capabilities, if there is limitation, towards the applications that give you the most benefit. And in order to enable such a evaluative framework, we need a lot of people, because we need policymakers and legal experts, because they need to force these companies to expose information about how regularly they train their model. Let's say ChatGPT is being frequently, let's say, updated, or Codex that runs basically Copilot, like it has a continuous learning process. What is the regularity of that, or some information about, like basically you need more information about energy consumption, carbon consumption, and operation of like these companies to do this kind of analysis. You need AI practitioners and engineers to provide support to measure these costs and benefits. Then again, economists, social scientists, civil society, and user, all of them are required in a different way to enable such an evaluative framework. And this can be used in wide range of ways, which I won't go into the detail, but I think you got an idea. So to summarize the lecture, basically we talked about sustainable computing. Demand is growing. We need to serve the demand sustainably. Energy efficiency gains were there, but they are reducing now. And then computing has unique advantages. We can try to optimize carbon efficiency and reduce operational embodied using multiple methods that I talked about. And computing for sustainability is just to say that computational methods are being used to reduce emissions in other sectors. And finally, I presented my last work. And even though we are near time, I am here if anyone has any questions to ask. Yes.
Google ChatGPT thing. Like those are online and aren't really indexed in the web the same way that Google is. And also, how do you account for factors like when you Google, you find scientific content links, whereas GPT kind of, well, not GPT, you compare it with say Perplexity that summarizes the info and you don't actually click on bunch of links that lead to very.
Yeah, I mean, that is the problem. That is where like computer scientists can help in quantifying the cost. So there has been now research on, so previously energy consumption was being monitored at most like data center level or industry level. Then there was a server level information. Recently, there was an interest in assigning energy to individual processes or VMs and applications. So I know it is going to be very hard with these microservices, serverless, and whatnot. But theoretically, you could trace everything and assign, because now you have the capability to assign power consumption of a server to a given process. And once you have that, all the other things such as carbon, and they typically remain the same for a given location. Like, right, for a data center, they are the same. So then you basically, what you need, the key ingredient is fine-grained energy measurement. And if you can do that using where the links are going and how they are being processed, like, it is a complex task, I'm not saying, but theoretically you could do that. And for some applications, it may be easier to do than the other ones. And over there, the comparison would be easier. But we one challenge is that with this kind of framework is that not all the costs or all the benefits. Let's say if someone uses ChatGPT to write a joke, and if they are a comedian, that joke is worth a lot to them. But how do you quantify the value of that joke? So some of the benefits and some of the costs may be tangible. Some costs may be harder to quantify. So that is why you would do this analysis, but define scopes and boundaries around your analysis. And that is where you would state that within this comparison, we just consider these, and costs. And any secondary or tertiary costs, we could not quantify or something. Yeah.
And the context of ChatGPT, Ford obviously like much more expensive and from the environment, but sustainability, but like in practice, even though people don't consider sustainability environment or any other ways, they do them cost. So often, like data pipelines, they go through like GPT 3.5 to like reduce the volume and then pass it to GPT-4 as a bigger search part, but it is a final result. So in a way, it's kind of, do you not think it's already quantified the way
Not really. So there are multiple things. Like in a lot of other sectors, the incentives and costs, they are aligned. Like, for example, if I need to buy a car and a car offers me certain incentives in terms of the luxury it has, the mileage it gives, and whatnot, and the cost is directly borne by me, I pay certain amount to get that luxury. But in computing, with a lot of, like, for example, Google search and all of those, the costs are borne by different elements. So if you are using ChatGPT 3.5, for a user, like, there is no incentive to be frugal or with Google search and things like that. For a company, there is incentive, but it doesn't mean that they are navigating it in the best possible way. So ChatGPT and the other reason is that for a lot of like these companies, performance is treated as the key kind of primary metric, even when it does not affect end-to-end system application performance. So you must have heard the debate around like training a model for face detection to 95% accuracy consumes 100 units of energy, but 96% accuracy consumes 150 units of accuracy. Now that model may not give the similar 50% improvement in performance when you actually deploy it to the application. So the point here is that there are cases where performance is being, or the giving the faster solution or the right solution is being prioritized in the current structure where it may not even be needed. So over there, this kind of evaluative framework can quantify the end benefits and then see what are the costs that should be allowed or expected. So it's like, I think it depends on, I hope I answered the question to some extent, but just the high level thing is that just because a company is doing something, it doesn't mean that it is the most environmental friendly thing. And also the current structure is generally around cost or performance. and they don't always align. Their effort to reduce energy consumption or cost may not be resulting directly in less carbon or less environmental impact. But yeah, I am happy to talk, like, if for the people who came late, this is my email address. Feel free to send me an email if you want to talk about any of my research work. I am happy to do that. Okay. Thank you.